talking about polynomial functions, but today we are just going to take it one step further. So we have a recap of old vocabulary. I'm not going to run you through all of these. Make sure that you have all of these vocab terms written down somewhere within your notes. Filling in these two blanks here though, a polynomial function is a monomial or a sum of monomials where the exponents are all whole numbers and the coefficients are all real numbers. Okay, so make sure you guys have all of these terms written down somewhere in your notes. All right, example 1 here. State the type of zeros contained in the following polynomials of least degree. Also, are there any functions that have double zeros? Okay, so in order to figure out the amount of zeros, so finding the number of zeros and the degree are two slightly different things. So the first thing we're going to do is try to find the number of zeros. So that is the amount of times your graph crosses the x-axis. In my first one here, I'm going to have 3 zeros. So, and they are crossing the x-axis, so I can write 3 real zeros. Okay, I can confirm that this is the degree of my polynomial by counting the amount of times my graph changes from positive to negative slope. So I have 1 as it's heading up, my second degree is as it starts declining, and then my third degree as it continues up towards the positive direction. So I can confirm this is a third degree. Okay, my second example here. First of all, as you can tell with the zeros, this graph never crosses the x-axis. Yet, this doesn't mean that we don't have any zeros. So for this one, I'm going to start by stating the degree. As you are heading from left to right, I start in the negative direction, but then it changes at this relative minimum and starts heading in the positive direction. So with 2 changes in sign, this is a second degree polynomial. So that tells me that I'm going to have I'm going to have 2 zeros within my polynomial here. But since it never actually crosses the x-axis, these zeros are imaginary zeros. So I have 2 imaginary zeros. All right. So we're going to save those last 2 for class. Try them on your own. Try to figure out what degree the polynomial is, and then try to talk about the zeros. Okay, example 2 here. Relationship between factors and zeros. So x minus c is a factor of a polynomial. We already talked about this with integral coefficients. If and only if c is a 0. So what we're going to try to do here is we're going to fill the table at the right by listing each factor and its corresponding zeros. Okay, so remember, your factors are, so let's take a polynomial for example. If I give you guys x squared plus 5x plus 6 equals 0, you guys are able to factor this. You guys would factor this as x plus 2 times x plus 3 all equals 0. Set both of these equal to 0, and you would get x equals negative 2 and x equals negative 3. Okay, this is the process that we already covered. So your factors would be this step right here, and your zeros would be your third and final step. So if I gave you the factor of x minus 11, your 0 would be setting this equal to 0 and solving it. So your 0 would be positive 11. If you set 3x plus 7 equal to 0, you would subtract your 7 and divide your 3, and you would get a 0 of 7/3. Okay, now we're going to work the other way. In order to get x equals -4, you would have to add the x back over, and your factor would be x plus 4. Okay, remember, this is just a review. Anytime you get a 0 of 0, that means that you had a factor of just x. Okay, finally, 1/2. This one is a little more difficult to see, but obviously, to get 2 as your denominator, you're going to have 2x, right? So then you divide your 2, yet we still need a positive 1, so we're going to have 2x minus 1. Okay, this is kind of just a reverse way of thinking about solving for your zeros from your factors. Okay, we're just going to run through these common types of polynomial functions and the names that correspond with each type. So if we have a degree of 0, we call this a constant. Okay, remember a constant is any number to the 0 power. So if I wanted to write this out longhand, I could write y equals -3x to the 0 power. Obviously, any variable number, etc., to the 0 power is just 1. So this is the same as saying y equals -3. -3 would be my constant. It would form a horizontal line. Okay, the next type of function that I have would be a linear function. That's with degree 1. So an example of that would be f of x equals 2x minus 5. These are the lines that you guys were graphing ever since middle school. Okay, second degree polynomials, which is what we just covered, is called a quadratic. Okay, a quadratic, you guys are used to seeing these. That's when you would have something like -x squared plus 4x minus 3. Okay, this is a quadratic. It has a second degree. A third degree is called a cubic. Okay, a cubic is when you just add one more power. So an example would be y equals -4x cubed plus 2x squared plus 5. Remember, we don't need every single exponent down. Your type and your degree are all based off the largest exponent. So then finally, a fourth degree, we call this a quartic. Okay, an example of this would be y equals 5x to the fourth power plus 3x squared, and we can just leave it like that. Okay, it's important to note, any degree that is larger than 4, we just generally call it a polynomial. Remember, a polynomial is in standard form if the terms are written in descending order of exponents from left to right. So your highest exponents are going to be on the left, moving towards your lowest exponents to the right. All right, on to the back side here. So decide whether the function is a polynomial function. If so, write it in standard form, state its degree, type, and leading coefficient. So remember, in order for us to have a polynomial function, we need to check, are our exponents whole numbers? Right? In example A here, I have my exponent of 2, 3, and 0 for my constant. We're all good to go there. Now I need to check my coefficients. Are they real numbers? I have a coefficient of -1/4. That's a real number. 1, and then 3. So we're good to go there. So the first thing I need to answer is yes, this one is a polynomial function. So the first thing I need to do is write this in standard form. So I need to write this from highest degree to lowest degree. So I'm going to start with h of x equals, my highest degree here would be my third power. So I'm going to write this as x cubed. My second highest degree would be my x squared, so minus 1/4 x squared. And then my lowest degree is just my constant, plus 3. Okay, my degree, that's the next question here. Remember, your degree is just your highest power. In this case, my degree would be 3. Okay, the type, you may want to refer to your table for the type of function. This one's a third degree polynomial, so this one is called a cubic. And then finally, my leading coefficient is the coefficient on my first term. I have nothing out in front, so it is assumed that we have a coefficient of 1. All right, so you guys will continue the process. Try B and C on your own. We will go over them in class just to make sure you are on the right track for both of those. All right, the next section here is evaluating polynomial functions by direct substitution. So you can substitute the given value in for x and solve for the output of y or f of x. Remember, every input is paired with exactly one output. So you will only get one answer for the output. Okay, so in example 4 here, for each function, determine its degree, leading coefficient, number of zeros, and end behavior. Then evaluate with the given input. Okay, so let's start going down the list here. First thing we need to find is the degree. Okay, remember, your degree is just your highest power. In example A here, my highest power is 3. Okay, the second thing I'm going to try to find is the leading coefficient. So my leading coefficient is my coefficient on my first term. So in this case, I have a leading coefficient of -3. Okay, the next thing we need to find is the number of zeros. Remember, your number of zeros directly aligns with the degree of your polynomial. So I have a third degree polynomial. That means that I'm going to have 3 zeros. And then the final thing I need to find is my end behavior. Okay, so for the end behavior, you need to write as x approaches positive infinity. Then my function, which is p of x, approaches blank, and we'll fill that in. You also need to have as x approaches negative infinity, p of x approaches blank. So this is where that table from the previous lesson really comes in handy. So in this case, I have an odd polynomial, degree of 3, with a negative leading coefficient. So we know that that is going to start in the positive direction. So as x approaches negative infinity, our function is going to approach positive infinity. And as we head towards positive infinity, we are going to approach negative infinity. This is something that you guys are going to have to memorize throughout this chapter. All right, the final thing we need to do here is evaluate our polynomial with the given x value, which in this case is x equals positive 2. So we have p of positive 2 equals -3 times positive 2 squared, cubed, plus 2 squared minus 12 times 2 minus 5. So this is just our substitution step, and now we're solving. Okay, remember all of your exponent rules here. So I've got -3 times 2 cubed, which is just 8, plus 2 squared, which is 4, minus 12 times 2, which is 24, minus 5. Just going to multiply this. So -24 plus 4 minus 24 minus 5. which would finally give me P of 2 equals negative 49. So if I was to graph this polynomial, when I would have an input of 2, my output would be negative 49. So this right here would be a point on my graph. All right, so once again, I know 5.2 is loaded with a ton of new concepts. Hopefully you guys were able to follow along for the most part. Please bring a ton of questions to class, and we'll plan on filling in the blanks in the notes. All right, thank you guys for watching.